Hello everyone, my name is Nandita Goyal. I am working as Assistant Professor in Department of Information Technology at ABES Engineering College. Today I will be covering the topic Posets. So this is the outline what we will be covering in today's lecture. First we will have an introduction to Posets, then we will be discussing a few examples on Posets, then we will be discussing what is totally ordered sets, and then Foset diagram. So to start, we will first discuss what a partial ordering relation is. So in order to come across the term Poset, first we will come to know what partially ordering relation is, then we will move to Poset. So a partial ordering relation is one that holds three properties. The first one is it should be reflexive, the second one is it should be anti-symmetric, and the third one is it should be transitive. So if I talk about reflexive, a relation is reflexive when it contains all the diagonal elements. Suppose if I have a set A which contains the elements 1, 2 and 3, so a reflexive relation must contain all the diagonal elements corresponding to this set, that is 1, 1, 2, 2 and 3, 3. Then we can say that that relation is reflexive. Now when we talk about anti-symmetric, in an anti-symmetric relation, there should be no pairs of the form, like if I have an element A comma B, then correspondingly it cannot have B comma A element in that relation. But if X comma X element is present, that is allowed in anti-symmetric relation. And the last one requirement is it should be transitive. That is, if we are having an element of the type A comma B and B comma C in the relation, then it should also have the element A comma C. So if all these three properties are present, that is, it is reflexive, it is anti-symmetric and it is transitive, then we can say that the relation is partial ordering, and the set on which such a relation is defined, that set is known as Posit. So we will be taking the first example, that is, if I have a set A with elements 1, 2 and 3, and I have a relation which is defined as 1, 1, 2, 2 and 3, 3. So first of all, we will emphasize that whether this relation is partial ordering or not. Now see, the first property, that is reflexive. So this relation is reflexive definitely because it contains all the diagonal elements, that is 1, 1, 2, 2 and 3, 3. So we can say that this relation is reflexive. Now talking about the anti-symmetric relation, since it contains only the diagonal elements, there is no element of the type A comma B and B comma A, so we can say that this relation is anti-symmetric. Now if I talk about transitivity, so just see, is there any element of the type A comma B and B comma C? No, because there are only diagonal elements. So we can say that this relation is even transitive. So since this relation is reflexive, anti-symmetric and transitive, what can we say about the relation? That it is a partial ordering, and this set A is a poset. So this is the notation for a poset. I have a set A for which relation R is defined, and if that relation is partial ordering, we can say that set A is a poset, and this is the notation for poset. That is the name of the set, then semicolon, and then name of the relation enclosed within square parenthesis. So now we have already seen that this relation is partial ordering. Now we will just see that this is also an equivalence relation. So for a relation to be equivalence, it should be reflexive, which we had already seen that this relation is. It should be transitive, which we had seen that this is a transitive relation, but it should be symmetric as well. So symmetric means that if I have a pair of type A comma B, then there should be a pair B comma A. If there is no pair like A comma B, then it's okay and the relation is symmetric. Therefore, we can say that this relation is even symmetric. So since it has the properties, that is reflexive, symmetric and transitive, we can call it as a equivalence relation. So this is a relation which we can call as partial ordering as well as equivalence relation. And just make a note of it that this is the only relation that can be categorized in both the categories, that is partial ordering as well as equivalence relation. And this is even the smallest relation which is going to be partial ordering or equivalence, because if you remove one element from here, that is, suppose I remove 3, 3. So what will happen? It will lose its reflexive property. So it will neither be partial ordering nor be equivalence, because for both of them it requires to be reflexive. So we can say that this is the only relation which is both partial ordering and equivalence, and this is even the smallest relation having both the properties. So now to proceed, I have just made a note of it that this is also the smallest equivalence and partial ordering relation which is possible for a set with 3 elements, that is 1, 2 and 3. Now see, in second example we have removed the pair 3, 3. So what happens? It fails to be reflexive, and since it fails to be reflexive, we cannot say that it is equivalence, neither we can say that it is partial ordering. So what can we say? That this is the smallest possible equivalence or partial ordering relation. Now let's take the third example, that is we have the same elements 1, 1, 2, 2, 3, 3, and a third element that is, and a fourth element that is 1, 2. So what happens? This is a reflexive relation because set A has only 3 elements, that is 1, 2 and 3. So all the diagonal elements are present. We can say that this is a reflexive relation. Now talking about symmetric. Is this a symmetric relation? No, because we have a pair of the type A, B, that is 1, 2, but we don't have the pair 2, 1. So we can say, since this 2, 1 is missing, this is not a symmetric relation. Now let's talk about anti-symmetric. Anti-symmetric, why? Because all these are diagonal elements, so no problem. And for 1, 2 there is absence of 2, 1. So we can say that this is a anti-symmetric relation. Now talking about the transitivity. Transitivity, if I have this element 1, 1, that is A, B, then I can say that this is of the type B, C. A, B, B, C. So it should have A, C element present. So what will be the value of A, C? It will be 1, 2. So 1, 2 is already present in the relation. So here I have transitive relation. And another pair which I have is 1, 2, that is A, B and 2, 2. A, B, B, C. So it should again have this pair 1, 2 which is present in the relation. So we can say that it is a transitive relation. Now since it is a reflexive, antisymmetric and transitive relation, it is a partial ordering. Now this is the fourth example for partial ordering relation, or we can say Posets. Set of all real numbers defined on the relation less than equal to. Why it is going to be a partial ordering? Reason being, the operation here is less than equal to. So all the diagonal elements will be present 1, 1, 2, 2 for all the real numbers. So it is going to be reflexive since it will contain all the diagonal elements. Now if I talk about antisymmetric, if it has a pair A, B, that means A is less than equal to B. So it will never have B, A pair, because it is never possible that B is also less than equal to A. So it will have only one pair, either A, B or B, A. So it is going to be antisymmetric. Next is transitive. If A is less than equal to B and B is less than equal to C, then we definitely know that A is less than equal to C. So if we have these two pairs in the relation, that is A, B and B, C, then definitely we will be going to have A, C in the relation. So it is always going to be transitive. Therefore we can say that set of all real numbers under the relation less than equal to is going to be a Poset. Now next we will be discussing totally ordered sets or linearly ordered sets or chains. How these are different. Now see, for these we will be working on posets only. We will be having as examples posets but with some additional properties. So a poset A defined on relation R is called a totally ordered set if every pair of elements in A are comparable. That is, A is related to B or B is related to A for every A and B that belongs to A. It means that if we have some elements in set A, then every pair of elements must be comparable. So either it will contain A comma B in the relation or B comma A. If this property holds, we can say that it is a totally ordered set. For this, let's take a few examples. The first one is, if A is a set of all real numbers, then the set A with the relation less than equal to. Now if we take any two real numbers, so either we will have A comma B in the set, A comma B in the relation, or we will have B comma A in the relation. So for any two elements, we can say that there will be an entry in the relation. So that is why we can say that it is a totally ordered set. Now coming to the second example. The second example is a set A which contains the elements 1, 2, 3 up to 10. And the relation is defined as A less than equal to. Now this is again a totally ordered set, because if I take any two numbers, suppose I take 1 and 3, so 1 is less than 3. If I take 10 and 1, so 1 is less than equal to 10. So for any two numbers, I can use this relation that is less than equal to. So every two numbers will have an entry in the relation. So we can say that it is again a totally ordered set. Let's take one more example. That is, if we have a set A with these elements 1, 2, 6, 30, 60, 300, and here the relation defined as divides. Now see, if I take any two elements, can I say that this divides relation will work? Yes, in this case it will. Because see, if I take 1 comma 2, 1 divides every number. So 1 will be comparable with all the numbers. Now if I take 2, 2 divides 6, 2 divides 30, 2 divides 60, and 2 even divides 300. So that means it will work for all the numbers. Similarly, 6 divides 30, 6 divides 60, and 6 also divides 300. 30 divides 60, 30 divides 300. 60 divides 300. So you take any pair of elements and you can place a divide symbol between them. So it is again a totally ordered set. Now let's take the fourth example. A set A with elements 1, 2, 3 up to 10, and we have the relation divides. Now see, 1 divides every number, this is okay. But if I take 2 and 3, can I say that 2 divides 3 or 3 divides 2? I cannot place the divide symbol over there. So that is why I can say that 2 and 3 are not comparable. There are many others also. So what can I say about it? That it is not a totally ordered set. Next example, we have taken a set S that contains the elements 5, then set A, set B, set with elements A and B. Then this subset. Now see, if I use the relation subset, phi is a subset of every set, so it will be comparable with every element. But if I take A and B, I cannot say that set A is a subset of set B or set B is a subset of set A. So these two elements are not comparable. So we can say that it is not a totally ordered set. Now let's take the last example for this. S contains phi A comma B, A comma B comma C, and we again use the same relation, that is subset. Now here phi is a subset of every set, so phi is comparable with any of the elements. If I take A is again a subset of AB and subset of A comma B comma C. If I take AB, I can again say that AB is comparable with AB and C as well as with all the other elements. So it is a totally ordered set. So now we will be talking about Poset diagram, which is also known as Poset diagram. So now Poset diagram is used to depict a poset. So there are a few rules through which you can draw the nodes and the edges in the Poset diagram. So now suppose I have a poset A with a relation R. The Poset diagram is as follows. First thing which we need to remember is there is a vertex corresponding to each element of A. Whatever elements we have in set A, there will be a vertex in the Poset diagram corresponding to that element. Now next we have an edge between the elements A and B is not present in the diagram if there exists an element X that belongs to A such that A is related to and X is related to B. Now it wants to say that this thing, when the edge will not exist. Now see, I have the element A, B and C. Now these are transitively connected with each other. A is connected with B, B is connected with C. That means A is connected with C. It is always going to have this A comma C element in the relation, because we are already saying that it is a poset. So since it is a poset, it is always going to have diagonal elements. It will always have transitive relationship. So when we have this transitive relationship, we are not going to show this edge from A to C. Reason being, we are already showing the edge from A to B and B to C. So there won't be any edge from A to C directly. So this is what the second point says. Moreover, there will be no loop since the relation is going to be reflexive. That means all the diagonal elements are present. So we won't have a edge from A to A. That is, we won't be having any loops in the poset. An edge between two elements A and B is present if A is related to B and there is no element X that belongs to A such that A is related to X and X is related to B. So again it is insisting on the transitivity, that we will have an edge only from A to B and B to C. We are not going to show any transitive edges. Okay. So we will take an example. See, I have a set A with elements 1, 2 and 3. The relation is less than equal to. Okay. So for this relation we have these elements, that is 1, 1, 2, 2, 3, 3, 1, 2, 1, 3 and 2, 3. Now I want to draw the Poset diagram. So how many elements I have? I have 3 elements. So I have shown 3 elements, 1, 2 and 3. Now see, we are not going to show 1, 1, 2, 2, 3, 3 because there won't be any loops. Now starting with 1 to 2, this is the relation. Then again from 1 to 3 and 2 to 3. Now if I check about the transitive relation, then AB, okay, B, C. That means 1, 3 is automatically there. So 1, 3 we are not going to show because of transitive relation. So what all edges I will show? I will show from 1 to 2 and then 2 to 3. Now just make a note of it that there are no arrows in Poset diagram. We do not use any arrows in Poset diagram. The convention is that the elements which are at the bottom, they are related with the elements at the top. So this automatically shows that 1 is related with 2, okay, and then 2 is related with 3. So we are not going to show any arrows, just the level will show you that the element at the bottom will be related with the element at the top. Now this is again a second example for Poset diagram. Suppose I have a set S that contains elements 5, set A, set B and set containing the elements A, B. The Poset is defined as S with relation subset. Now how we are going to draw the Poset diagram? I have 4 elements, so I have drawn the 4 elements. Now see that phi is related with every element. So phi is related with A, phi is related with B. Phi is transitively related with A, B. Now A and B are not related with each other because they are not subsets. So they are at the same level. We have shown that there is no relation. Phi is related with B, phi is related with A. Now A is related with AB. Again B is related with AB. So we have shown it this way. So that was all from my side for Poset. Thank you.